Welcome back. This is Mr. Hassan's Maths channel. I'm now answering question number 4 from the International A-Level Edexcel Core Mathematics C34 paper from January 2020. Now this question here is also question number 6 for my end of topic worksheet. For my Pure 3 end of topic worksheet number 2, the modulus function. This is from my Cambridge collection, and one of my students at school has asked me to go through this question, so I thought I would record the video. In fact, all he wanted was part C, but I'm going to go through the whole question just to make sure that it's understood and complete. Now, so for part A, we're asked to sketch the graph with the equation y equals the modulus of 2x minus 7 plus 1. Now, the sketching of modulus graphs is something relatively new in the Cambridge syllabus, something that was introduced in 2020. Before it was just solving equations, but now we have to sometimes sketch the graph of these modulus kind of equations. So first thing that you have to understand, when they ask you to sketch a graph, in your mind you should picture what type of graph it is. Whether is it a linear graph, is it quadratic, is it cubic, is it reciprocal, what type of graph you can be able to picture what it should look like. So when you have a modulus graph where you have these absolute value symbols, or this, these two vertical lines and expression within those, then you should understand you're going to end up with a type of graph, which in most cases, if we have a linear, if we have a linear graph, okay, or a linear equation, we're going to end up with something that has this type of V shape to it. All right, so either this way or upside down, there will be this type of distinctive V shape kind of to the graph. So in this case, we can see we're going to definitely have a V shape. In front of the modulus sign, there's no negative. Therefore, it's going to be upright V. It's going to have that type of shape. So that should be in our mind that we're going to have something like this. So the other thing we should think about is how to find where it crosses the two axes. In this case, they only ask us to find the minimum point and the place where it crosses the y-axis. Okay, so let's first think about where it would cross the y-axis. Now, a graph crosses the y-axis when x equals 0. When x equals 0, that's where the graph any graph will cross the y-axis when x equals 0. So to find where it crosses the y-axis, to find the y-intercept, we're going to replace the x with 0. So you have so y equals the modulus of 2 times 0 minus 7 plus 1. So here we're going to understand what happens when we have a modulus. Okay, so 2 times 0 is 0, minus 7 is negative 7, but that negative 7 is within the modulus bracket. So that means basically that the output of anything that goes inside a modulus bracket will always come out as positive. So if it's positive, it stays as it is. If it was 7 in here, it would come out 7. If that was just 7, it would come out 7. But it's negative 7, it also comes out 7. So anything that comes out of a modulus will be the same value, but just positive. The same magnitude. It's basically asking for the magnitude of this number. How far away is it from 0 on the number line? So if you think about here's 0, and here's negative 7, and here's positive 7, both of them are the same distance away from the number, from 0 on the number line. They're both 7 units away. That's all they're looking for. It's how far away it's from 0 regardless of the direction. So this is 7, negative 7 becomes 7, and you got plus 1 on the outside, so you end up with 8. So we can see that the y-intercept is going to be 0, 8. That's when it's going to cross the y-axis. And the next thing they told us to find is the coordinates of the point where the coordinates of the minimum point of this graph. So as we can see, it's going to have this minimum type of point. Now to find the minimum point, it's very similar to how we deal with quadratics. All right, because if you think about it, the modulus symbol acts like a bracket that's squared, because the output of something squared will always be positive. The output of the modulus sign will also always be positive. So basically, the lowest that this expression can ever reach, which will be the minimum point, where the minimum point is when you have 1 plus this. This is like 1 plus the modulus of 2x minus 7. Now this thing is, you're always going to add something to 1. And the thing that you add to 1 is always going to be positive, because whatever comes out of this is positive, right? So you'll never be taking away anything from 1. So 1 will be the minimum point for the y. And what causes us to not add anything to the 1 when this becomes 0? So when 2x minus 7 becomes 0, then this, what's inside here, becomes 0. And then you're left with 1, which is the lowest that it can ever be. It can't ever be lower than that. So when x equals negative, that's going to be 7 divided by 2. So x equals 3.5. So the minimum point is going to be when x is 3.5 and when y is 1. So we have the minimum point and the y-intercept, okay? Those two things we have now, and it's now very easy for us to make a sketch of the graph. Now, a sketch does not mean a proper, full-blown kind of, diagram or axes where you have all the points marked and everything. No, it just wants a sketch with them, with the important points. Here, the important points are going to be the place where it crosses the y-axis and also the minimum point. Okay, so it crosses the y-axis at 0.8, and the minimum point was 3.51. 3.51. So that's going to be 1 here, and that's going to be 3.5. Okay, somewhere over here. Okay, so it's going to go through these 2 points. So let's draw the line like this and like this. Okay, going to have this up. The gradient should actually be a bit steeper, really, if we're going to, we don't have to do 2 scales. So what I'm going to do is, I'm just going to make it a bit steeper by doing this and moving that to there, just to make it look a bit steeper, right? So it's like a gradient of 2, more realistically. It doesn't really matter if you don't, but I think that makes it just look slightly more realistic. Okay, so there we have the the coordinates of the y-intercept, all right, and the minimum point, which is 3.5 and 1. So that's the graph of y equals a modulus of 2x minus 7 plus 1. Okay, so that's that graph drawn. And now part B says solve the equation 14 minus x equals the modulus of 2x minus 7 plus 1. Now there are numerous ways for us to solve this equation. Okay, you can just go straight into it. For example, what you could do is say 14 minus x equals the modulus of 2x minus 7 plus 1. This has 2 different possibilities. You can leave it exactly as it is. So 14 minus x equals, and you can say 2x minus 7 plus 1. Just get rid of the modulus sign without any change to any signs. And then you can have 14 minus x equals, and everything inside the modulus sign will change its sign. So instead of being 2x minus 7, it will be minus 2x plus 7, and then the plus 1 on the outside will stay as is. All right. And then you can go about solving these 2 equations, and you'll get 2 solutions. Okay. So you can say, for example, here you're going to have 14 minus x equals 2x minus 6. So we can add x to both sides. So 2x plus x equals 14 plus 6. So adding 6 to both sides, adding x to both sides, 14 plus 6 is 20. So 20 equals 3x. So we end up with x equals 20 over 3, which you can say is like, that's 6 2/3. All right. That's the x. Basically, that's the x solution. That's the value of x that solves this equation. Or we can also, the other solution will be 14 minus x equals minus 2x plus 8. So we're going to add 2x to both sides. So that'll be 2x minus x equals, you have 8 minus 14. So x equals negative 6. Okay, so those are 2 solutions. Now, what we should make sure, because when you're solving these equations, it's possible for us to get solutions which are not actually real solutions. Now, if I go back to our graph that we drew, there's a way for us to be able to tell whether we're going to have, any full solutions. And that is by drawing the graph of y equals 14 minus x on the same axis as what we've drawn. So if I draw the graph of y equals 14 minus x, that will be a graph that goes through 14, and it will have a gradient of a negative 1. So it's going to be a shallower graph than this graph. So of course we can see that I will definitely cut this line in 2 places. So it's going to be shallower than this graph. So there's going to be 2 places where it cuts the graph for sure. Okay, one of them was my minus 6 and 2/3. The other one was our 6. So we can see that these two solutions must be true. Okay, this is basically the solution we got when we got the positive argument of this graph, which was 2x minus 7 plus 1. Where is it? 2x minus 7 plus 1. When this is the one which has a negative grid. It will be minus 2x plus minus 2x. And this would have been minus 6. Okay, minus 2x plus minus 2x plus 6 plus 1. Minus 2x. Yeah, sorry, this would be minus 2x plus 7 plus 1, which would have been minus 2x. Oh, sorry, this is the positive argument. What am I talking about? This is, of course, the positive argument. It's a positive gradient. So this would have been as it would have been 2x minus 7 plus 1, 2x minus 6. Where does that meet this graph, which is y equals 14 minus x? When you equate those, you get this answer here. And this, of course, is a negative argument when you get y equals minus 2x. And you're going to have plus 7 plus 1, that's plus 8, which would be this graph here. And you can see definitely they're going to meet. So we can know that these two solutions are correct by looking at the fact that these two lines will definitely intersect in two places. Okay. Now, if you didn't draw the second graph on here and you weren't sure whether one of the answers would be true or false, then you can check your answer by taking this and replacing the x with your x value and seeing does it make the equation true. Okay, so if you take 14 minus 20 over 3 for one side, and the other side will be the modulus of 2 times 20 over 3 minus 7 and then plus 1. If they give you exactly the same thing, then we know that this is a true solution. So 14 is something over 3. 3 times 14, 30 plus 12, that's 42 minus 20 over 3. That gives us 22 over 3 on this side. And here we're going to have 40 over 3, modulus of 40 over 3 minus 21 over 3, plus let's put 3 over 3 at the end so we can add everything together. So 40 minus 21 is going to give us 19. 19 over 3 plus 3 over 3 is also 22 over 3. So we know that that's correct. Okay, because the modulus of 19 over 3 is going to be 19 over 3 plus 3. So we know that this is a true solution. And we can do the same with this. We have we have 14 minus x, so 14 minus minus 6 on this side is equal to, well, we'll see if it's equal at the end. We're going to have 2 times minus 6 minus 7, okay, modulus plus 1. So this is going to be 20 on this side. And here you're going to have minus 12 minus 7. Okay, that's a minus 19, but in the modulus sign, plus 1. Well, that give you on this side 20, because negative 19, the modulus sign comes out as 19 plus 120. So we know they're the same. So therefore, we know that both of those are true solutions. So if you're not going to sketch the other line, okay, then you should check to see if your solutions make the original equation true or not. If it doesn't, okay, then you know that one of those is not a true solution. And you can find that, you can think about how would you get something that's not a true solution. For example, if I have a line that goes like this, I'll just draw it in different color, just so you can see the cases where a solution might not actually be a real solution. Okay, if I draw a line like this, for example, okay, so put the color blue, okay, like this. Now, this line will cut this curve only in one place, as we can see from here, right? It only cuts at this one place. However, if we solve this equation algebraically without thinking about anything else, we would also get a solution over here. We'd also get some solution down here somewhere. This line and this line cut each other, and this line and that line will cut each other in two places. All right, so you can see here that this, if we continue this line on, there would be two solutions. And if you solved the equation of this line and one of these two, in this case it would be the 2x minus 6. If you solve them, okay, together, it would give you a solution. You'll get an answer, but the answer is actually not really there because this curve turned up. This line turned up over here. It didn't go that far. But algebraically, you'll get two answers. But the answer that would be incorrect would be an answer which does not satisfy the equation. There will be something that comes out either with different values, or you end up with saying the modulus of something equals something negative. There will be something wrong with our showing that they intersect. Okay, when we try to see if the values are true, there will be something wrong with that answer that's not right. Okay, that's why it's important for you always to check. If you sketch the graph, you can see. You don't even have to check. But if you didn't sketch the graph, then you have to be careful, okay, to make sure you check to see that your equations are true. All right, so that's very important to make sure to verify that our solutions are correct. You should always either substitute, okay, your answers into the original equation, or just make a quick drawing of that line on the same graph, and you can see definitely they're going to intersect in two places, or they'll only intersect in one place, for example. Okay, so there's the answer for part B. Now for part C, it says an equation or a straight line has equation y equals a half x plus k, where k is a constant. Given that L does not meet or intersect this, y equals the modulus of 2x minus 7 plus 1, find the range of possible values of k. Okay, so in this case here, what we need to do, we can do this in many ways, but probably the simplest way is by actually thinking about the sketch. So I'm just going to do a quick sketch again of the original graph. Okay, so we've already worked out what we need to. I'm just going to do a quick sketch here. So we know that it crosses the y-axis at 8, okay, and it turns at 3.51. Okay, so this is the graph. So this is 3.5, this is 1, this is 8, it's not to scale, of course. This is a graph of y equals a modulus of 2x minus 7 plus 1. Now, y equals a half x plus k is going to have a gradient, which is a shallow gradient. So its gradient will look something like this. I'm going to draw it like different color. So it's going to have a gradient that looks like this. Okay, so this is y equals a half x plus k. Now k is going to be, of course, a place on the y-axis. So it says, given that the line does not meet or intersect this graph, then find the range of possible values of k. So we've got to find the case where it doesn't meet or touch this graph. Okay, so we know the vertex of this graph is 3.5 and 1. Okay, and this graph of y equals a half x plus k, we want to find the value of k such that this will never touch that point. So basically, we want to find what, when you put let's see, will this go through the point 3.51? Let's see. Okay, so we want to find what happens when x equals 3.5 in this graph. All right, we want to have the value of k such that it will never touch this point. So let's find out when it actually does touch this point. Let's see, when x equals 3.5, what is the y output going to be? So y is going to be a half times 3.5, which is 7/2 plus k. Let's do it over here a bit neater. So when x equals 3.5, y is going to be a half times 7/4 plus k. Okay, so you're going to have y is equal to 7/2, sorry. So 7/4 plus k. Okay, so now we want this to be, let's see, when will it touch this point? Okay, what's the value of k such that they will intersect at this point? Okay, so we want to find the value of k such that y becomes 1 when y equals 1. We want to find what k equals when y equals 1. So what we're going to do is we're going to replace the y with 1. So that will tell us what value of k is where they intersect. Understand? Basically, another way of thinking about this, probably an easy way of thinking about this, is we want to know when does this line intersect with or go through the point 3.51. So when does the line y equals a half x plus k go through this point? Okay, when does this point lie on this line? That's what we need to find. Okay, and that will tell us the value of k for where they actually touch. So if I do that, I put y equals 1 and x as 7/2. This is probably a better way of thinking of it. So you have 1 equals 7/4 plus k. So k is going to be equal to 1 minus 7/4. Okay, 1 minus 7/4, which gives us, that's minus 3/4. Okay, that's 4/4 minus 7. So it's actually going to be down here somewhere, actually, if we drew it properly. It's actually going to be down here somewhere. It's going to be something like this. Okay, so it will be somewhere down here. Okay, that will be how the graph looks. Okay, so the value of k such that they never touch, or they touch, is going to be when y equals, okay, when k, which is the y-intercept, equals minus 3/4. Okay, so now, if k is, if we make the y-intercept larger than this, if k is more than minus 3/4, then it's going to intersect. It's going to intersect the curve. It's going to intersect the modulus function. But if k is less than negative 3/4, if the y-intercept is below negative 3/4, you can see that this line will not intersect with this curve. So we want to find up to the point where it doesn't meet or intersect. So if k equals negative 3/4, it's going to meet, right? It will just touch the curve at that point where the curve, it will touch the modulus function where the v is, right? So if it's below negative 3/4, it won't touch. So for this, the k has to be less than negative 3/4. Okay, so that's how we answer the question. K is less than negative 3/4. That's the range of possible values of k. All right, if k is less than negative 3/4, remember k is the y-intercept of this graph. If that's less than negative 3/4, then it will always be below that and never touch it. Okay, so there's the answer to part C, which was the answer that the student was actually looking for when he asked the question. I went through the whole question just to make it complete. So I hope that answer is satisfactory. Thank you for watching. Other questions from this particular paper will be found in the playlist that will appear in the top right of this video at the end of the video. Other questions from the topic of modulus functions from my edXL collection can be found over here, and from my Cambridge collection can be found over here. And you can find in this playlist over here, you can find the other questions from this end of topic worksheet number 2, which this question is taken from. Thank you for watching and see you soon.